I've been losing my job for the past 3 years to this thing, and I have been doing this for more than 20 years. So is this really the end, like everyone keeps saying? I mean, it does a lot. It codes, it writes, it makes scripts. You can even use that Claude thing, which I still don't understand what anyone is using it for. But for the past 3 years, the message has been the same. I'm losing my job. Everyone says it with this strange sense of victory. The CEO says it, the people building it say it, they even have benchmarks. Apparently, it does everything better, faster, cheaper. And yet, somehow I'm still employed. So, how good is it really? To answer that, I didn't want to make another lab experiment. No fake problem, no perfect little metric, no clean setup where I gather some data and then pretend it proves something. I wanted to use it in a normal-ish scenario, a real project, a real specification. And one rule: I am not allowed to jump in and fix the code myself. So, I decided to run an experiment. The rules for the experiment are simple. I write a specification, pass it to the thing, and let it code. During the development phase, I'm not allowed to look at the code. I only judge the project from the user's perspective. Does it produce the expected behavior? And once the whole specification is implemented, I dive into the code and do a code review, taking a look at the architecture, code quality, reusability, maintainability, and other stuff. And the end result should be a reality check for some people. In the experiment, I used a harness that I created with a few colleagues. Under the hood, it was running Codex 5.4 or 5.5 on extra high in fast mode the whole time. Now, to be clear, this is not a scientific study, and I'm not trying to sell it as one. This is peak first-hand anecdotal evidence. But I'm pretty sure if we ran this experiment for long enough and gathered enough data, the results would still land somewhere in the same ballpark. And in the conclusion, I'll also talk about the limitations of the experiment, including the obvious argument that maybe I wasn't using the tool properly. But that's kind of the point. My goal was to use it the way the most non-technical or semi-technical people are trying to use it. Not like an experienced programmer babysitting every line of code, but like someone trying to get the machine to do the work for them. So let's talk about the interesting part. My findings. Now, during the code review, I noticed that some patterns kept showing up again and again, which I expected to some degree. So I decided to split the problems I found into problem areas. As you know, AI is not bad at writing code per se. It usually does make mistakes where the code doesn't compile and everything is obviously broken. The mistakes are more of a directional nature. What do I mean by this? It pushes the code base into the wrong direction, and then it keeps adding code on top to fix or mask the issue. So I'm gonna go through each problem area, talk about my observations, show actual examples from the code, explain what the AI did, why I think it's not good, how I would approach it differently, and most importantly, why I would do it differently. So let's start with the first problem area. The architecture started right, but then picked the path of least resistance. The first problem is not that the architecture started wrong from the jump. The project specification defined a client and server architecture. So, like in many games, we have a client and a server, and each one has its own set of responsibilities. So, at the very top level, the AI did not do the dumbest thing possible. It did not put everything into one local game loop where the player, server, network, UI, and everything else lives in just one file. That would be bad, like bad, like academic group project bad. But when you look into the implementation a level deeper, you realize the modules exist, but the client and server modules are just huge runtime files. So the client runtime is one file with about 5,000 lines, and the server runtime is one file with 3,600 lines. Now, huge line counts are not a crime, don't get me wrong. Sometimes there are reasons for big files. But here the line count matches the responsibility problem. So let's take a look at the client update function, because this immediately shows what I mean. Let's just take a look at this. So the first lines are timing. Bounded network macros, clock client frame counter, and that is the client clock responsibility. Then we have this drain incoming packets. This is networking, so packet receive and synchronization. Then we have combat traces, the kill feed. This is obviously combat, so it's not networking anymore. Then we have the prediction correction. This reconciles the local player against the server state. And then still inside the same update function, there's a whole replay capture lambda. This checks whether recording is active, builds the view state, builds a render frame, creates the local player replay item, pushes the frame into the record buffer, and advances the recording timer. So in the first chunk of this update function, we already touched timing, networking, combat feedback, kill feed, prediction, visual synchronization, and replay recording. And this is my point. The code is not broken per se. The problem is that the responsibilities are bolted on top of each other in line. So every time the AI needed a new feature, it found the place where all the state already exists and just appended the next block there. Now if you scroll further, the same update function also gets into input handling, keyboard overlay, runtime settings, scoreboard, and bunch of other UI stuff. I don't need to show all of it line by line because it's the same argument. You get my point. Now, client runtime update is not reading like a high-level client update function. It is reading like the place where everything that can happen on the client side gets implemented right there. I mean, a clean version of this would still have a client runtime update, don't get me wrong. But the runtime update function should only be the orchestrator, where we have the implementation grouped in functions that carry the specific responsibilities. So something like this. So first we create the frame for that specific tick, then we do network sync, then update the combat, then do prediction, then if frame recording is on, we record the frame, and then process the input. Now this is of course not a real implementation, this is some pseudocode, but the point I'm trying to make is that the function now tells me the whole story of a frame. If I want to change client prediction, I go to the client prediction file. If I want to change the combat, I go to the combat file. I don't need to know that the replay capture starts around, I don't know, line 2067 and the UI mode starts somewhere later and that the scoreboard is hidden somewhere in a nested function. That is what I mean with architecture. We don't need anything fancy. Just knowing where to put the damn code is a real skill. But to know where to put the code, you need to know how to code. And that brings us to our today's sponsor, boot.dev. Generating and understanding code are not the same thing. Boot.dev is not one of those platforms where we watch other people do cool things for 10 hours. You can either go through the courses or jump into project-based learning, which, as you know, I always prefer over just sitting there and watching videos and pretending. And honestly, with AI everywhere now, that matters even more. Boot.dev has this integrated IDE, so you don't have to install anything. Just sign up and you're ready to go. If you open their catalog, you can find lessons like build an AI agent in Python, which is more useful than most people think. Learn memory management in C if you wanna be a real chat and go full fundamentals. Or how to find a programming job. And this is a real course, I'm not even joking. So use the code Tariq10x, use the QR code on screen or click the link in the description to get 25% off the monthly or annual membership. And you know what? It's risk-free, brother. Why? Because boot.dev gives you a no-hassle 30-day money-back guarantee. How about that? Now back to the video. So let's take a look at the server side. On the server side, the same pattern shows up. So I'm not gonna repeat now the whole argument, but for example, if you take a look at this function, server tick, you will see the same thing just on the server side. The first lines are clock and tick counting, then it applies a pending shot evaluation mode change, and so on. And don't get me wrong, all of these responsibilities are valid. The problem is that they are all implemented inline in the runtime tick. So the tick function becomes the place where every server feature gets attached. Now a better version of this would look something like this. So we have server tick, then we get the tick, then we do server runtime parameters, we apply the parameters before the simulation, then we do the simulation, for example, then we publish and record the events, then we do lag compensation, and then we publish a new snapshot, and so on. Now again, this is not real code, this is pseudocode before all the Stack Overflow mods start foaming. And this is crazy that we live in a day and age where I have to make this disclaimer and explicitly say this is not real code. But I guess we're living in a rage economy right now, like a rage and rage bait economy. Anyways, you get my point. The point is the split. The point is it's not good to put everything into one file and write everything out like inline. You don't need to have a daddy working at Blizzard to know this, okay? So the right move would be to refactor this and start at the top at the folder structure. So we could have something like this. A client folder with the runtime, clock, network sync, prediction file, replay, input, and so on. And then a server folder having all the server stuff in there. Like runtime, clock, combat, snapshot, blah, blah, blah. And now if I want to edit combat, I go into the combat file. If I want to edit snapshots, I go into the snapshot file. The folder structure already tells you where you need to look. That is the difference between code that works today and code that will stay maintainable over a long period of time. And this is where the Quake 3 comparison is useful. Quake 3 is 30 years old C code. But the big responsibility areas are visible from the file layout. Client features live in the client files and server features live in the server files. And then we also have this shared layer for, I don't know, player movement. My point is not that this project should copy Quake 3. My point is that 30-year-old game engines were aware of this concept. That now apparently the best coding machine ever that beats everyone on a benchmark seems not to understand. If a system matters, give it a place to live. In this case, AI did the first step right. It split the client from the server. But then it kept adding features to the biggest object in the room. And that is what makes the code feel bolted together. The runtime should tell the high-level story and not implement everything inline. And the details of that story should live in the files that own them. Now let's talk about software parameters, because this is one of those small software design things that gets ugly really fast. A parameter is just a value you want to tune without changing the code every time. Tick rate, snapshot rate, latency, packet loss, and so on. In Counter-Strike terms, this is the kind of thing where you open the console and type something like sv underscore parameter and some value. And that's the important part. The caller should say what they want to change. They should not have to build the whole message by hand. What the AI did here in the first step is actually understandable. It started by creating this generic parameter change request struct. Basically one small packet type that can represent many different runtime changes. Scope tells you where the change applies, target ID tells you who it applies to, key tells you which parameter you want to change, and value is the new value. So this struct is the client or UI saying, please change this parameter. But then the AI also created this other struct called runtime param snapshot. And it's basically the same struct again. I guess the idea was to separate two directions, but this is duplication. And this again shows you how the AI tends to think when coding. It keeps adding stuff instead of stopping for a second and asking, wait, I think I might have seen this somewhere. Okay, but let's ignore the fact that the AI created the same struct twice. The basic idea is not stupid. It is trying to avoid creating a new network message for every little setting. And it is trying to distinguish request versus snapshot. If you want to change the tick rate, snapshot rate, latency, whatever, it can all travel through the same generic structure. The part where this falls short is the rest of the implementation. Because after creating the generic struct, the AI did not create the API around it. There is no small runtime params file that owns the parameter IDs, creates the requests, validates them, and routes them in one uniform way. Which means every subsystem that wants to change a parameter still has to know how the struct is built and how it is supposed to work. For example, let's take a look at the diagnostics module. This function wants two things: set latency and set packet loss. But to do that, it checks the peer ID, casts it, figures out the scope, creates a vector, reserves two entries, builds two structs, calls this runtime param key for target, and writes the strings latency, ms, and loss PCT. So diagnostics is not just saying set latency. Diagnostics now has to handle the whole protocol. It has to know that a request needs a scope. It has to know that a target ID is an 32-bit integer. And it has to know how target keys are built. I mean, it has to know even the exact string names. And that is the batshit crazy part. I mean, if you're gonna do it like this, then don't even bother creating this generic struct, like for real. The better approach would be to hide this behind one generic helper function. For example, something like runtime params set param, and then we have like the ID, the target ID, and then the value. Internally, set param can still create the actual runtime param change request. It can still fill in the scope, but diagnostics should not build that protocol message manually. And now, since this mechanic is not centralized in one place, the same thing happens in the client runtime and every other subsystem that uses this. For example, here the client wants to change some parameters, but again, it has to do all this protocol thing manually. So again, the client runtime is not saying set tick rate, it is doing the whole plumbing around it. And this approach also makes it very error prone. Since the parameter identity is a string, so if one side writes, I don't know, snapshot rate with an underscore and the other side expects it without the underscore, the code will compile, it will kind of work. I mean, C++ doesn't really care. And it also gets harder to test because there is no unified parameter API. You have to test diagnostics building requests, then you have to test the client runtime building requests, then you have to test the server runtime dispatching these requests. And if another system wants also to use parameters, now it has also to do its own version of the same logic too. And as I said, this problem is spread out through the whole code base. I mean, if you open out the server runtime, you will see it also does the parsing. So the string knowledge exists in diagnostics, client runtime, server runtime, and everywhere else. Now the alternative that I would use here is very simple. So you have like this one file that defines all the IDs, and then in the same file you define the helper functions, and that's it. And then the server dispatch becomes this boring switch case. And I like boring code. Boring code is easy to understand, easy to maintain, and easy to test. And this is how these parameter concepts are usually implemented. So one place, one ownership that owns the parametrization of your software. Now again, if you take a look at Quake 3, it has, if you remember my Quake 3 video, the console variables. And the console variables live centrally in the console variables file. You have all the helper functions and all the stuff you need to work with console variables. And again, I'm not saying we should just copy paste the Quake version if you want to like implement parameters, but it shows you that this is not a like novel idea. That's something that's been around for a while. And I would expect a tool that breaks all the benchmarks to, I don't know, think about that when implementing parametrization. And when talking about parameters, just as I said, parametrization is not like a novel concept. You see the same idea outside games too. For example, cars have parameters for different markets. Same platform, but different configurations. You can have different like speed limits, I don't know, infotainment settings, and so on. And the last thing that you want is every subsystem inventing its own parameter format. You want one parameter system that says, here are the adjustable values, here is how they are encoded, and here is how they are applied. Okay, now let's continue with the next problem area. Logic leaking into session flow. The session flow controller is supposed to own the application flow. Supposed to. Host a session, join a session, advance the proxy, run the local client, leave the match, return to menus, and exit the game. But in the implementation done by this frontier AI model, it also starts receiving packets, parsing these packets, accepting clients, queuing commands, and forwarding payloads. Okay, so this function receives datagrams from the socket, then it deserializes packets, then it validates the protocol version, then it handles hello, welcome, reject, commands, disconnect, and generic control channel payloads. This is a lot of protocol ownership inside a session flow class. But let's be serious for a moment, okay? The immediate downside is that session flow becomes harder to test. If I want to test malformed packets or unsupported versions, I don't know, some other stuff like command routing, disconnect behavior. Now I have to go through a class that also understands session lifecycle. That is not where protocol tests want to live. And the likely cause why the AI implemented it like this, in my opinion, I'm not an AI engineer, is it was using the path of least resistance. I mean, the session controller already owns the hosted server pointer. It already has the hosted socket, it already knows the clock, it just knows everything you need. So the shortest path is to just put the packet pump here. This is of course not the optimal solution because of the things I mentioned. Now let's talk about solutions, not just like point out interesting implementations, how I like to call them. So the preferable solution, my opinion, is not complicated. I would just extract a like server transport adapter. It owns the receive, parse, route, and other functionality. And then the session flow controller only, well, controls the session, right? So something like a pump that receives the payload, and then something like a parser that parses the payload, right? And then the session flow code becomes, again, boring, which is exactly what I want from a session controller. Now, if I change the protocol, I go to the adapter. If I change the lifecycle, I go to the session flow. I don't need to touch the session flow every time I want to change the protocol. The boundaries become obvious, and that's what we should be striving for. As you can see, and as I told before, the AI again missed an opportunity to decouple things and make them more elegant. And instead, it went to this path of least resistance, and it kept adding code until it worked. It seems like to not be able to look at the problem from a broader perspective. Like it's generating correct lines of code, but it looks at a project like someone who never coded before or who doesn't understand how to structure things properly. Okay, now let's continue with the next problem area. AI missing on reusability. Now, since the NetcodeSimulator is a game, it's obvious that we have rendering everywhere. We have the actual like in-game character rendering, we have character thumbnails in the UI, and we have the character editor. So we're not talking about some random visual helper that's used only once in one place. We are talking about the same character appearance, being rendered in multiple places. And once again, the AI actually started in the right direction. It created a shared character geometry function. This function takes the character appearance and turns it into a little geometry model. This is good. The AI recognized that character appearance should not be manually interpreted everywhere. But then, once again, it missed the next step. It shared the geometry, but not the rendering of that geometry. So that means we now have 3 different places that more or less render the same concept again. So first we have the in-game renderer, which draws the character in 3D. Then we have the thumbnail. We have the same character appearance, same geometry idea, but now it is rendered into a 2D UI rectangle. And then we have the character editor that does almost the same kind of 2D rendering again, just like the thumbnail renderer. You already understand what it did. The AI made a shared geometry function, but then again, it started like in the examples before. Instead of taking a look at the whole picture and thinking, okay, what can I make more modular and reuse in other sections? It started like, let's just keep adding code, adding features, adding code, adding features until we get there. And one of the visual disadvantages is visual drift. The thumbnail uses one shoulder thickness value and the editor preview uses another one. Then the thumbnail uses one outline style, the editor uses another. I mean, you could now argue that's intentional or it's not intentional, but I mean, since the rendering is now split into 3 places, you have to maintain 3 places. If later on I want to change how shoulders are drawn or add, I don't know, hitbox visualization or make thumbnails and editor preview match exactly, I need to touch multiple files. And this is again the AI coding pattern. It solves the local task, but it misses the more reusable, more elegant solution. So a better solution would be something like this. We have this one rendering for a 2D character and one for a 3D character. And then the player 3D just calls this draw world character, and then the thumbnail and editor call draw character preview, which is the 2D one. The service owns the recipe. It knows how appearance becomes geometry, how shoulders are projected, how torso and head are drawn, and so on. And the caller then only needs to decide, do I want like the 2D or the 3D version? And that's it. And that's the silver lining. The AI created build character geometry, so it was like halfway there, but then it just stopped and was like, you know what, let's keep adding code, because that's what I'm good at. Conclusion. Now let's talk about what we actually do with all this information, where the experiment falls short and why I still think it is useful as a reality check. In this experiment, I tried to act like a non-technical person who got told by a CEO, we need to ship something by Friday. So I was not trying to be the senior engineer who constantly corrects the architecture, refactors the bad parts, and guides the AI into a clean solution. I wanted to let the AI build a solution mostly on its own, and then look at the shape of the solution afterwards. And yes, of course, this is anecdotal evidence. This is not a benchmark, but that was kind of the whole point. I wanted to see what happens in a realistic scenario, where the product can look good from the outside, the demo works, the features are there, but then you open the source code and ask, okay, what kind of software did we actually create here? So once the project fulfilled the functional requirements from a user's perspective, I stopped. I uploaded it to GitHub, link is in the description in case you want to take a look at it yourself, and then I started reviewing the code. And honestly, my opinion did not change, it just got amplified. AI can produce code very fast, and it can get surprisingly close to what you asked for. And if something does not work as expected, it is very good at adding more code until the thing works. For prototypes, experiments, and testing ideas quickly, that is genuinely useful. But if you're building anything serious, you can't just keep bolting things on top until the output looks right. At my job, for example, in embedded software, this approach would not survive very long. You have very limited memory, CPU limitations, timing constraints, and you gotta fulfill safety requirements. You cannot hide bad structure behind more layers of convenience code forever. At some point, the system pushes back. And that is what the code review showed today. The assistant can move fast and it can build useful features, but without architectural pressure, it tends to follow the path of least resistance. If one file already knows everything, it keeps adding more stuff to that file. If one subsystem already has access to all the state, then that subsystem becomes the place where the next feature lands. It reminds me a bit of optimization algorithms. If you ever worked with physics simulation or any kind of optimization problems, you know that a bad optimizer can converge very quickly into the wrong direction. It finds a local optimum very fast, it finds something that works inside the immediate solution space, but it never steps back and asks if this is actually the right shape of the system. And that is basically what happened here. The code converged, it worked, but it converged into a shape that is harder to maintain than it needed to be. And this is where the human developer still matters. Not because we are some kind of magical typing machines, but because a human developer can look at a code base, at a solution, and they can still say, yes, this works right now, but it is moving toward a bad structure. And that is the actual lesson. AI helps you move fast, but it will not automatically protect the long-term shape of your code base. You still need someone who understands ownership, boundaries, testing, architecture, and the cost of future changes. Because shipping the first version is one problem. Living with the code afterwards is a completely different animal. Okay, now I want to take the moment and say a big thank you to my Patreons and YouTube members. If you want to support the channel, you can become a Patreon or YouTube member. A link is in the description. So leave me a comment. I want to hear your opinion, your experience on this type of projects. And if you like the content, hit like and subscribe. That's it for today. See you in the next one. Tariq 10x.